fact, we just had a great conversation about AI, and I'm now going to be joined by two great experts and veterans of the industry. It is my pleasure to introduce Javier Castellar and Brian McClendon. And with that, Javier, would you like to introduce yourself to?
Yeah, I'm Javier Castellar. I'm one of the founders of Asolon. We have been very focused on military simulation with sensors for literally 27 years. But we came from the same place that Brian came. And there is a lot of hidden world of history of Google Earth from his part and Asolon for many years. We started training humans, but we are training humans and machines today. So it's a very interesting spin and reuse of technology. And our focus right now, or the next thing, is basically building real-time, live world databases with models behind that allows you to do all the missions that you need to do at a scale, at a global scale. That's probably a good summary. Yeah.
Okay, yeah, I think Javier's given me a chance to give more of the history. Tim had a beautiful slide that had a lot of the NVIDIA history, and my history and the history of Javier and myself overlap that quite a bit. So I started at Silicon Graphics in 1988 and built hardware for 8 years. These were the original GPUs, and the team that built that hardware eventually, folded into AMD and into NVIDIA, and many of those folks are still at those companies today, working on the newest architectures. But the thing that really brings us all together, I think, is my first ITSEC was in 1995. And we brought this new texture-mapped 3D polygon machine called Infinite Reality. It was, in fact, a refrigerator. It was big, 6 9U VME boards to do one graphics pipe. And it did 100 million polygons per second, textured. And so, that's a great benchmark. But we realized that to get that kind of power out of the graphics and onto your eyeballs, you need a lot of really good software. And so we had OpenGL, which was a start, but not good enough. We had a library called Performer at SGI, which was our sort of visual simulation library that many developers used. And there was one set of developers in particular that was currently at SGI at the time. We called them the Three Spaniards, and that's one of them.
Ex-Spaniards now.
And they developed the most amazing demonstrations of what was possible for flight simulation, and we showed that in a Whisper Suite in 1995. And at the time, people didn't believe it was going to happen. It was, we weren't going to use graphics workstations. They had to be bespoke flight simulators, and pilots would only tolerate errors beyond a certain level. But as many of you know, things changed. And we released that hardware, and it did over $1 billion in business, probably much of it driven by users of Echelon, which started and built on top of Performer and then made everything you see today from an amazing company there. I then left and started a company called Intrinsic Graphics, which then started a company called Keyhole, which was then acquired by Google in 2004. So Keyhole, many of you know, but we were a small little name, and that was the code name of the company, not the product. And so we sold that to Google because Google had the ability to buy more imagery than we could afford. And when we released Google Earth in 2005, it kind of changed everybody's idea about what 3D graphics and possibly even what visual simulation could do, because it put 3D terrain graphics textured into everybody's hands. And it became very popular very quickly. We built a Google Maps with it as well. We started to collect street views, so now we had ground collects. We started an aerial program, and Google had and has still 60 planes flying, and that's how you get your 3D reconstruction of urban areas, and it's also how you get the stereo terrain of the rest of the world from these higher flying ortho imagery airplanes. But Google also integrated satellite imagery. And so building a single holistic 3D model of the world turned out to be very valuable. Like having the answer for every pixel on Earth has a lot of appeal, both visually and to consumers, but also to commercial and military customers. And so we did it for consumers, and Javier can talk a lot more about what he did for his customer base. Since then, a company was formed at Google called Niantic Labs, and they spun out in 2016 or 2015, and in 2016 released this game called Pokemon Go. And back in 2017, 18, John hired me to help with this new idea of AR mapping. And so I rejoined John Henke, and we built an AR mapping pipeline using large amounts of ground video data. And so with that, we have built a visual positioning system, and we're very focused on precise location derived from pictures that you take. That system was part of Niantic Labs, but just this year we sold Niantic Labs to a gaming company, and I am now part of what's called Niantic Spatial, and we are continuing our work to do localization of using visual positioning, both from ground scans, but also from aerial and satellite data, and trying to help you localize where GPS does not work as well. So that's a long, long history.
So no, but that's really cool that you guys actually worked together way back then. So now fast forward, technology's evolved. We're talking about training humans and machines, and you guys are collaborating on that space. So
Yes.
tell us how that came to be.
So it's very funny because what happened is where they were doing this, I would say, unclassified thing, we were doing the multi-spectral equivalent of Google Earth for the military use. And we end up probably taking over most of the market as of today for the high end, right? For simulating sensors. Our claim to fame in ITA was, we started a company, we are going to be doing geospecific, physics-based, multi-sensor simulation worldwide. EOIR, radar, at a scale to serve training and mission rehearsal. So we spent our lives doing that. And then the moment that they spin off and became geospatial platform, Niantic Spatial, we text Brian, like it was literally a text. He's like, okay, so now you are willing to work with the government too, right? Through you guys. Like, yeah, okay, perfect, because we need precisely where they were working. We were trying to start doing that because we need, we were doing already for 11 years AI-based approach to extracting from multispectral satellite imagery 3D content. We were extracting all the trees, all the houses, like at a scale for actual missions, right? But what we were missing is that was the old way of thinking databases. It was missing the model underneath. Yeah, we can do black body emission, reflection of energy, radar, but what we wanted was to jump from mission rehearsal with very fast pace for special operations or for other uses to live monitoring. When I mean live, I do mean live. And for that, you need a big backbone of models that are beyond a world model as a classic database, but it's a model that understands the world. And what they have is actually different than a world model. It's a large geospatial model, very different story. And funny enough, we were very complementary. We decided to announce Project Orbion on September 9th to the press, which is unusual for us. We never do press conferences. And saying, hey, I think that we can use this, will help the defense side, but also we can do it for dual use, for emergency services. Because our blood boils every time that we see damage in Texas from flooding. When we know that we can collect with space-based radar, with unclassified sources, every 10 minutes, changing floodplains. Or we see a fire in California and other states. We could help all those people, but if we combine commercial sources, and then we have some groups like us, mostly military focused, other groups are more broad of dual use, we can help the country and the proper allies. And that's the final reconnection, which is crazy to say that now.
That is incredible. I recently spent time in the geospatial analytics world, and it's near and dear to my heart, all of those examples that you just described. And it's been also for the constellation operators, there's always the need of a killer app, right? And I think you guys are kind of heading into that. So Brian, talk to us about large world models. Is it semantic based? Is it physics based? Is it everything? How do you think about that?
Very good. Yeah, we saw Tim from NVIDIA speak about large world models, and they have a large amount of data, and they've built this capability to effectively synthesize frame by frame the real world at some level of quality and have the physics accurate and have it visually correct. But one of the things that I think we're not seeing with large world models is geospecificity, mapping, like the map. Like if you look at how the world models think about it, they don't think about the underlying structure of the real world. And for years, at Google and for years at Echelon, building that 3D accurate reconstructed model of the world is fundamental to how you present it, because you don't want to falsely train people when they are trying to see what the world looks like right in front of them. So the large geospatial model trains on a combination of ground truth, ground collected data, aerial data, and other data sources. But at the end of the day, its goal is to accurately reconstruct, localize, and semantically understand in 3 dimensions any place in the world. And we're not done with all that yet, but the goal is to be able to provide that semantic understanding to the kind of databases that Javier has been working with, but also to be able to reconstruct from much less data the real world, and do so hopefully in real time, very, very quickly, and provide it back to consumers who need to see what was happening 15 minutes ago, not 15 months ago.
And one interesting thing on industry, that was a great question on the industry side. So what is hard to realize is that beyond the military side that we understand, the fact that at the beginning on the Keyhole and Google Earth thing, everybody was saying that it was impossible. That data will be too expensive, the data is only controlled by the government, nobody has 1 meter data for the world. Of course, that triggered space image, starting to commercial sources that were unclassified and available to use. Their work triggered all these new space companies that are out there are because there was a killer app called Google Earth that triggered all these new companies with constellations of satellites. What has happened more recently in the last few years, and that was part of what triggered this relationship and some of the follow-up over the next 2 years, is that there are not only new sources of data as we understand for static, there are sources that are high revisit day constellations. So you have both Bantor, you have Black Sky, you have revisit dates with constellations of hundreds of satellites, not few dozens. But the second part is not only electro-optical, is radar, space-based radar. And that's critical to help to train some of the models. So what we are doing, for example, right now, and one of the enabling factors that enable this idea that may look far-fetched, but is actually available, we have demonstrations today in the show floor, is space-based radar. Right now, you take, let's say, a constellation from ITSEC. They have 62 satellites today, capturing 15 centimeter, 16 centimeter data with radar that contains phase. Anywhere in the world, about every 10 minutes, depending where you are. What that means is it penetrates clouds, it penetrates smoke. That allows you to continuously monitor initially targets, but of course scaling to objects. And that allows a richness of detection that can fit beyond the resolution of the pixel of the radar with models that understand the world to get something that is literally real time or very close to real time. We are starting with maybe every 10 minutes, maybe every hour, but we are not far away. I mean, as the constellations, especially for radar, space-based radar increase, you are going to end up in a few years with the entire world with energy on the ground, which means global GMTI, global ground mounted target indication, but forget about targets. We are talking about continuously rebuilding. And imagine how critical that is to know in the fire in Palisades, to know in real time which houses are down or up, where you should send the firefighters. But there's a military use, that's pretty obvious. But what I'm trying to explain is the same perception that this is far-fetched, that a live, worldwide, multi-spectral world is possible, was the same resistance that we encountered at the time. I remember the marketing people, they didn't believe that you could do geospecific flight simulators in 95, etc. In fact, they were refusing to put it on the booth in the exhibit floor. The Air Force ended up sending, from the Air Force Research Lab in Mesa, they ended up sending all our infinite reality devices, and we were flying what it was impossible in the lobby on the Marriott in Orlando. That's how far the resistance was, because the perception of databases at the time, it has to be vectorial, or it has to be non-geospecific. What is happening right now is these databases are no longer one way. There is a loop in which the more you collect, the more precise the collect is, the more you can reproduce the database. When you apply this to the drone problem, the answer to a swarm of drones is a counter swarm. But it's not homogeneous. You send ISR first, collect, and rebuild for the next wave. So it's a continuous rebuilding. That's the concept that is important. These are not your classic static world. And for that, you need a large geospatial model because it has to be automatic. It cannot be human-based. Now, when you get to the human base, you end up understanding, okay, is this door opening outwards or inwards? That's kind of important for some people, right? So, but that's what I'm trying to say. This is not a far-fetched thing. This is not years away. These things are here. And the reason because people don't realize this is because it's coming from completely different markets. SGI was coming from a different market, from the Vitals, the Medallions, etc. So it was a cross-pollination. You were coming from the left field, or the West Coast in that case, right? Out of the blue. This is the same case. It's just it's coming from very advanced geospatial people doing space-based radar. Space-based radar is kind of a weird concept for most people. So it's surprising that this is possible. So start thinking on databases as a continuous loop. It's what we call AI at the time of need. It's time-based and it's continuous. It starts slowly in terms of the rate, but these constellations, they're launching 20, 30 satellites a year right now for space-based radar. When you combine that with what these guys are doing, and by the way, you need also the ground thing. These guys are doing incredible 3D reconstruction, right? And with high precise centimeter-based BPS, with no GPS. That is what you need both. You need the space-based seed plus the ground continuously being updated. And that allows you then to have your drones, to have absolute high precision, live rebuilding of the battlefield. And expanding to electronic warfare, radar. I mean, this is not just one band of the spectrum. We are talking about multi-sensor, multimodal at a scale.
Yeah, so there's a pattern of cross-sensor and fusion of multiple sources, right? Mm-hmm. And it's interesting to see that it's not just from different modalities of collection, but also commercial and very fit for purpose, defense centric.
And that's how you fund it. That's how you fund it.
Right.
You get the commercial people to pay for it, and the government gets a fixed fee price, and we are all happy.
Some of the commercial people say, well, we'd like the government to pay for it.
It's true. It's a true statement.
One of the things that we learned with Keyhole and Google Earth is that it's, for us, coming maybe from the outside as a provider, breaking into the government and getting people to buy Keyhole back in the day, 2002-3, was very difficult. The moment it went on television and their kids were showing it to them, in their living room, it completely changed, right? When your kids have a better platform for visualization than you do and that your pilots do, that's a problem. And so I think the advantage of commercial is that it can put things. It breaks through the mindset much, much faster. And so I think one of the biggest changes that we're seeing, that I think we're going to see very shortly, is that when we did SGI back in '95, we were introducing textured polygons to visual simulation. And it took a little while, but that took over to this day, more or less. NVIDIA loves ray tracing. That's another modality. But I think we're seeing a different one coming, which is Gaussian splats. And Tim mentioned a little bit, but we see Gaussian splats as a new way to render and visualize 3D geometry in a much more compelling way at performance speeds. Yes. And I think that's really the operating path. It also is an opportunity to carry data into the future. Textured polygons are very long in the tooth. They don't do well with semantics. They don't do well with segmentation very well, but with many of the new models coming out for segmentation, they operate very well on Gaussian splats. And so I think we're going to see a migration of at least some parts of the database into Gaussians versus textured polygons. And you may have both, But for visualization and semantics, I think Gaussian is a winner.
So, and while you're on that topic, again, I'm a recovering geospatial intelligence guy, and one of the things that was pretty clear for us is, well, training a model to segment and, basically classify optical, great, because we as humans know to say this is tree, this is grass, this is ocean, right? But how are you guys combining this with SAR, which is traditionally very hard for humans to decipher?
So with training perception models, self-driving cars actually taught us a lot, which is that, it's very hard to label LiDAR data with human car or whatever, but it's very easy to label pixels and the video that the camera's doing. So the Waymos of the world collected both, very large amounts of it, labeled the pixels with human help, eventually with computer models, but then learn that to the LiDAR. And for the most part, they only do perception with LiDAR in the field. They could do multi-sensor, but for most part, their LiDAR alone is good enough to do all of the segmentation, object recognition that you see in self-driving cars today. And I think that's going to be true here as well. That having the optical and labeling, and we have a lot of really great models now for labeling optical. But then transfer learning that to the other sensors, I think, is going to enable them to be just as good.
So for us, it's interesting because the way in which we are reusing the assets that we have. So we were building all these things for sensors, precisely because they had to correlate. It was a correlation problem for training humans. You needed the OIR, you need a head-mounting queuing system for the pilot, night vision goggles, infrared, even LiDAR, all kinds of things. What we have discovered is, if instead of putting on the display system, we pipe it into the inputs of the mission computers of the autonomous systems, we create the matrix movie for the drones.
Interesting.
And then you can train millions of hours with all the iterations of weather, no weather, air turbulence, no air turbulence, on all modalities, on all sensors at once. And by training them, that allows you to literally allow pure sensor fusion with precision of all the sources. So what we do is, there is an important distinction, which is the difference between the data and the database. Mm-hmm. So the data source, many people say, oh, this database is made with satellite imagery. No. This database starts with satellite imagery, and then many other things happen. You are merging stereo extraction, photogrammetry, with SAR, etc. What happened is, because we were building radar simulators, in fact, we even bought a company doing an entire team to use just radar simulation, not for training humans, for training machines. Because if you are able to simulate the sensors that you are trying to fuse, you can create the framework for the live sensors to have an almost perfect fusion for real-time applications. And that's the key, is the fact that, in fact, there's a funny story on this. When we started the company, we were foreign nationals. Now we have high clearances. It's a completely different environment. But because we were foreign nationals at the time, we couldn't see the sensor responses. We have to develop our sensors physics-based, which means that now we can do, even though now we're in the classified world, the black world, special access programs, whatever, we are able to render the simulation that you need to train the ISR asset to recognize the actual feeds and correlate them together. Mm-hmm. So this is a very funny reason why it's possible, and it's completely accidental. It's not that we are more clever. It's
right.
as if we stumble, but
necessity
for our path, right?
Necessity is the mother of invention, right?
It was, that's how it happened. Really.
And since I'm glad you touched on, training machines, because last year here at NBT we had a few sessions, and we have a few again this year talking about human-machine teaming. Like, this conference is ultimately not just simulation; it's training as well, right? And so, can you guys talk a little bit about how you think about training machines and how your collaboration unlocks value there?
Yeah, I think one of the biggest things, and Echelon has already figured this out, is that the biggest consumer for this data long term is machines versus humans. We'll be training humans till the end of time, but machines are much harder to train. They need a lot more data, a lot more repetition, but they can also train faster. And so can you provide the large amounts of data needed to train these machines? And in our case, one of the first problems that some of these sort of naive machines struggle with is, where am I? And localization is hard, and so you can either put a lot of hardware on there and hope, or you can use visual positioning to give these machines an idea of where they are, and then use other kinds of odometry to keep track of it over time. But that initial position and that sort of ongoing location is needed more by machines, because they don't have the human intuition to look at the street sign, figure out the intersection, and guess that they're at the corner of 82nd and 5th Avenue. They have to, the machines have to have something much more precise about where they are. And so I think location matters. Eventually semantics are going to matter much more, real-time semantics, and also the semantics of the world around you that you can't see. In a lot of cases, your best exit is behind you, as we hear on the airplanes.
And there's an interesting silver lining of training the machines, that the databases that you use to train the machines become the baseline to give the context for the human to understand the data that you get back from the machine. Because we are building simulators all the time, we just reduce the simulation capabilities for humans, in which we are experts on. We are running the soft floor, 8K 240 Hz, 7 channels, for example. Live field displays on vehicles. All kinds of different advanced displays. Barrio, mixed reality systems, for example. But we can reuse those assets that we use to train pilots for the humans to fully comprehend in a natural way, which is through the eyes in stereo, to comprehend the returns in mass from the AI. So it gives you, so the human understanding of how vision works, actually, and the experience from which this came from somehow, accidentally, graphics, computer graphics, is very useful at the PED, at the exploitation level of ISR, but it's also important for the commander to understand what the hell the AI is doing with thousands of drones, because we are talking about thousands of drones, not hundreds, not dozens. And that's the beauty, that with the same investment, you cover engineering simulators, trainers for humans, training for machines, mission rehearsal, live monitoring, and a natural way of understanding what AI is doing. But it requires models underneath. And I think that's the beauty, that in a single pop, you're hitting all these three buckets. If you don't have the correct human interface at a natural perception level, you cannot exploit or take life and death decisions. Even in automatic killing chains that are starting to come in, you still need a decision maker with enough framework understanding to understand with all the sensors at the same time, if that's the case. The other aspect is collaboration. So typically you will have the allies as well at once. You need multi-level security working simultaneously on the same war room, in which the Americans are looking to a different view of the sensor. The other people is seeing a completely different level of security at the same time for decision making. So decision making and the other loop to be shortened to very quick is fundamental to be paired with the AI aspect of the problem. And I don't think that is fully understood, the scale of how many drones we are talking about, how many types of drones, and how these databases are being built on the fly all the time. That's what, that level of finesse that you need underneath with Niantic, the new type of sources of data, that's what enabled this. And there is an urgency to do this, by the way, or a duty to do this. Of course, it's very beneficial, valuation-wise, whatever, but this has to happen because other countries that are not friendly are probably doing the same. I mean, this is not, we are not geniuses here, okay? So that's the important aspect. So it's very strange collaboration of human machines, then what we used to do in DOMs, now we can use it in the field. It's a very interesting loop of
and brings a whole new definition to the OODA loop, right?
Yes.
Now, I recall from our conversation that you guys had an interesting thing that you did for the Coast Guard. You want to talk a little bit about that?
Right. So one of the things that we have had, a lot of people, some of you may have, out of curiosity, how many of you have ever had used the app Scaniverse? So we have like 3, 4, 5. You don't count, you.
You don't count.
So Scaniverse is a free app on your iPhone and Android that allows you to capture a object typically or a scene and reconstruct it in 3D. And it can reconstruct a mesh, and you can export the mesh. But it was also sort of our launching pad for exporting Gaussian splats. And so we were one of the earliest providers of Gaussian splats pretty much anywhere. And we also created the SPZ file format, which is now more or less de facto standard for how you send splats around. And one of the things that we realized is that we can, the fidelity, visual fidelity of the scenes we capture is much higher than what's typically out there, especially from aerial collect. And the one area where there's the collision between the aerial and the ground collects is helicopters need to understand the neighborhood of where they're landing very, very precisely, because the keys that they look at to understand, am I close to the ground, what's the space around it. So Coast Guard is interested in getting a much higher fidelity collect around their landing zones so they can train their pilots to land in these sometimes very difficult areas. And so we are providing ground level collects to integrate with the rest of the flight.
And it's an interesting thing because we were already doing pretty much all the simulators of the Coast Guard for all their platforms, right? And the Coast Guard is a great service because first you can do things at unclassified level more and faster, and they're very flexible. They're willing to try things, right? They don't risk anything when we were paying for it. It's no big deal. But for them, we can test this on the simulators first to see if it makes sense, because maybe it's a bad idea. So the idea behind is you're going to go to a new landing zone in Alaska, and this is very common. It happens all the time. I mean, I don't know if you know, but you're talking about 24,000 people saved every year by the Coast Guard. Many times they cannot go to places, even though we have built the databases with the very precise landing zones in very complicated locations with very poor visibility. And we have probably pretty up-to-date landing zones where they normally rescue people. However, it changes, especially in Alaska. There's snow, there are things falling on the ground. And there are many accidents. Even with the best pilots in the world, you still have trouble. So one of the concepts was, well, we take a system, you're able to scan the area by the end user, by the destination guy, the guys that are going to rescue, or the people around him, to capture the area, send it back to the center, and before the takeoff, they are able to understand the landing zone. Also, these days, we can compute computer fluid dynamics in real time on the GPU. We can compute for the prevailing winds the sad air turbulence of the area based on the obstacles around. And then they fly in. That's an example. The good thing is that because they have a unified training center, the Coast Guard always train all in mobile. No matter where you are, if you are in the Keys in the Bahamas or you are here, you are able to test in their site with the right pilots. The same pilots are going to fly the mission. And the idea was, well, next year we start deploying this as a test base, just a test, and make some real examples and evaluate. Because the good thing on this is different than building a website that you can fail 10% of the time. The website doesn't work, no big deal. This is a life or death thing. It has to be vetted by the real people. We start in the simulators in a safe environment and move it to the field. And eventually will be taken over by the current contractors, ASI, whoever is there. But this is a very good thing because it's very important to test these things on the real world, on the military, or in this case, the Coast Guard. But the Coast Guard typically is a relationship with, of course, Homeland Security. And it's a perfect place to try this instead of going to a highly classified environment in which doing this, just getting the permits to do this would be impossible. So that's the beauty of having, many people complain about the federal government sometimes, but there are heroes out there in all services that are willing to take the risk of testing something new. Not widely, not putting people at risk. And that's the way to go, because you are talking about something that could save lives every year, right? And we decided to do this, and we are definitely doing it on many levels.
That's incredible. You're basically enabling near real-time mission planning and rehearsal.
Yes, it's a very short. So it's like we do, I will not mention regiments, but we do a lot of the SOCOM component, right? This is similar, but it's closer to the mission. This is like before departure. Now, you could conceivably do it while you are on the fly, while you are flying towards the area. But there's no reason why we couldn't do that. In fact, we have discussed that too.
And
so
in the
it's
scenarios
possible
where
to get on the loop. Yeah.
a unit gets pinned down and you need to send a QRF, they can basically say, here's the situation around here. You have real-time situation awareness on the ground.
Yes.
That's incredible.
Yeah.
That's incredible. Folks, we would like now to open this to a chat with you all. And so if you have questions, please use the microphone.
I have a couple questions. I'm super interested in what you're talking about. So the first question I have is, in a world model that understands the satellite image, the ground level, the skies, the weather and so on, where do you draw the line from inside to outside? Do you want to understand the inside of certain buildings too? Of how specific do you want to go indoors? Because I see a lot of use in that area, especially at the consumer level.
Yeah, so I
The perfect person to answer exactly.
Indoor is much more consumer and enterprise. We have seen a lot of enterprise interest in modeling businesses or industrial locations, and I think having a single model to rule them all is not yet there. To solve your problem in particular, I would very much focus on sort of the outdoor versus the indoor, because it turns out indoor has a lot of very special cases that you really want the model to understand, but you don't want the outdoor model looking for the upper corner of the room, because it turns out that localizing yourself indoors is very bad from a GPS perspective, but it's very good from having detail in all 6 sides of the cube effectively.
Okay, my second question is if you have a planetary scale AI making planetary scale decisions, you need to have a planetary scale understanding of uncertainty and risk, especially when lives are at stake. And what type of mechanisms do you think can achieve that, or that are kind of moving towards that direction of understanding, I don't know what I'm looking at, because we can't predict everything in the world when it comes to the end of the day. So how can you handle uncertainty and maybe when to fall back and say this is not reliable?
So that's where we got very lucky, because we have been building, I would say, any target that probably matters for the allied nations, we have built it for the trainers. So at least we have a good start. So unlike like he was describing, it's very easy to go in the streets of San Francisco and capture data on video. It's very hard to get that in North Korea, right?
Yep.
So, but we have been simulating North Korea all our lives, right? And we have simulating their vehicles and their trees and their water and their tents and everything. So there is an advantage because for decades we have been getting information beyond what you collect from ISR to train the model. It's not perfect. However, we do know the concepts more from ISR of what is the probability sphere of 90%, right? That's our typical standard. What is the precision probability of location of a point in 3D in the world around your pixel or your post of the building? And then we know that is, let's say, 1.5 meters, 90% probability that that location in a global database, full world database, is between, let's say, 1 meter, 1.5 meters, 3 meters, for example, is more typical these days. So there is an understanding of that level. In some point, that's where you absolutely need the continuous loop of the database. What I was describing is the first wave may have less information because you don't have the area yet with the latest up-to-date data. The second wave, every loop that you do with ISR or missions, attack missions, you are able to collect more data that decrease the uncertainty. Now, the rules to manage that, when you can take the decision, that's a separate topic, even at legal level, right? Like, so there is a legality on certain decisions on the military side that is questioned also.
There's an interesting, when I started in geospatial, somebody told me, oh, there's this thing called WGS 84. And I thought, well, that's a surfing competition. No, it's the World Geodetic System that dates to 1984. And Earth isn't round, it's an ellipsoid, it's an approximation, right? And every year we get better quality sensors, we can refine the model more and more, right? And so to your point, like what we're going to see in 5 years is considerably different than what we see today.
And for example, most of the simulators that use hardware in the loop, in which you have a aircraft display computer and things of that sort, we learned the hard way that that's not enough. You need the geoid of the Earth. So we have to use the true geoid, centimeter level precision, to actually portray things that are valid for a real mission at low level. So that's how crazy it gets. So you need centimeter level, at least the mathematical model of the surface versus the altimeter has to be precise enough, because in our case, we encounter that every day because all the military aircraft, you have typically to use a classified mission computer and a classified device that feeds on real data. And when you cheat the data, it better be with the shape of the Earth. And the shape of the Earth is not WS84, it's EGM 98, right? And it's crazy. It's a crazy, and you have suffered that even more. Than it is crazy how complicated it is.
I have a lot of opinions on this. The world changes dynamically, right? There's these, continental drift is a problem, and earthquakes are a problem. But the biggest problem with the world is humanity. Humanity does not stand still. It knocks trees down, it builds buildings, it knocks down buildings. And so your 3D model, the closer you look at the world, the more you need to update it and the more you need to understand it and to keep it accurate. And so, at Google, when we started with, 1 meter satellite imagery or 15 meter, Landsat imagery, we had an update from 10 years ago and people said, yeah, that kind of looks about right, but it's 15 meters per pixel. We put 1 meter imagery there and people started to complain that their house wasn't there because it got built in the last year and a half. That was news. Now people are complaining that the backyard extension with the deck and the 2 chairs, is in the wrong place. And they're complaining about that. That's the consumer complaint. But in this industry here, it's much more important to have a very recent, very updated 3D model of the world, and then being able to explain that to people and show it to them.
And gravity is not uniform. So we are talking about that the ocean, you have a tilt, and we account for that on the simulators. We have to account for that. And that's what gives you the advantage, because you need absolute geolocation for life and death decisions. And it has to be a continuous loop, because even the actual map of the Earth in which the normals of the gravity change, and the oceans have these weird shapes, so you go in front of the Indian Ocean, you have this depletion of 80 meters down, 80 meters down, when you go very far away. But new sensors can see extraordinarily far away, so you have to account for that, even though it changes a centimeter every 100 kilometers, right? So there are things like that that are not obvious, but the beauty is, because this has been addressed already, the missing thing is the continuous loop. And these things actually change. It's unbelievable. For that level of precision in which you're trying to minimize collateral damage or hit a specific thing, the line of sight when you are on the limit of your sensors is absolutely 3D, is very strange shapes, the math gets crazy, and it took us decades to get it right, and it's a learning, and you start saying, why this is not working? Sometimes noise, things that we think that are noise on the sensors happens to be a gold mine, right? So there are things like that are very strange, and especially with radar, when you start to go the radar way, it gets even more extraordinary, because nothing hides from radar. You can see day or night, but you see any changes in terrain at the scale, and then you learn that your baseline was not correct. So it's the ground truth is a tricky business.
Garbage in, garbage out.
Yes.
Right?
Yes.
Do we have another question from the audience?
Hi, Brady Barrett. I'm in the Space Force and spent some time with the NGA and focused on a lot of systems that look down. In government areas, especially the ones that we focus on, we're maybe starting to think about those things that are horizontal or up. And it's amazing here to see all the applications. Of course, a lot of these are military based, and then there's things that provide a tremendous headwind to military applications. But in the space realm, we find ourselves perhaps a little bit more isolated. And so one of the questions I had is, one, are there many commercial endeavors that you know of that deal with that? Of course, you can't play Pokemon Go in space. So there's some headwinds that we face just in the limited number of engagements there, but I think that was true probably for a lot of the applications that we had that you talked about to begin with, where there weren't commercial applications until there was. And so, one, do you know of anything that's starting to think about the orbital regime, or lunar, cislunar, and all these things that we know are coming? We don't know on what time frame, but then for someone who is trying to, rather than understand geography in a machine-readable world, perhaps the orbital regime in space in a machine-readable space, because all simulation we have to do, we've been so focused on providing air, land, and sea effects that now that we have to protect our own domain, we realize we have to serve ourselves a little bit to further those capabilities. And of course, there's other forums where we can talk about different things, but I think it's appropriate at this level to talk about commercial and what partnership we might see, or does it have to be a government first mover?
I mean, I think this isn't really a legitimate commercial one, but there are now commercial people talking about sort of lunar missions and so on. And so lunar navigation, lunar orientation, lunar mapping, we've got pretty good maps, right? There, in some ways, we know way more about the surface of the moon than we do about the bottom of the ocean right now. And so can we do visual positioning, because at the moment there's no GPS satellite up there orbiting the moon telling us exactly where we are. And I think that is one where what we're doing on Earth's surface could apply to the moon as well, because there are a lot of very sharp edges on the moon, and they're also relatively unique, which is a powerful thing.
Yeah, we did actually a study of repurposing our engine for the moon. The problem with the moon is there's something called mass stones, right? Which is areas of higher density, so there's not a stable orbit. And then the good news on the commercial space on that answer is a lot of the new constellations, let's say Starlink, I will not talk about derivatives of that, but let's talk just Starlink. They have now laser-based communications. Laser-based communication needs a perfect understanding of the position of the aircraft. So because it's commercial and they have to point their lasers to get the full secure communication, that already puts the framework for inter-orbit imagery at precision on the spot. So you don't want to, and normally radar will be probably better sometimes, but you are able to, in the commercial space, they already have the full, with 7,000 satellites, they're already pointing to each other in space because the laser links. So most likely derivatives related with the Starlink, when they add other things, maybe the appropriate thing for defense in orbit, because it's funny, those calculations are the key. And even on the Earth it's tricky. In the moon it's even harder for what we analyze, how there's not a stable orbit. I mean, it's just crazy. So I would say that that's the initial model, because then it's easier to point sensors. If you are pointing a laser with a very narrow beam, you should be able to point out the things and have a continuous, because you no longer have an enemy satellite anymore. There's going to be a swarm of satellites. There are going to be thousands. So it has to be, same thing with the drones, you need that environment, all the math model, all the targeting training to do synthetic. You cannot train 1,000 drones in red flag. You have to do it synthetic. It's what we call synthetic reality. So one model will be, you see what we did on F-35, right, on the Joint Synthetic Environment for F-35, very successful program. It's emissions-based, right? You're testing hundreds of devices. So there's equivalent to that for a man. It should be an equivalent GSC for space. That's my opinion, and that's the right environment.
That's great to hear, because the Space Force has made initial small investments for the joint simulation environment to understand. Hey, instead of geocentric or
very familiar. Oh yeah.
Incorporating everything, how do we do this? And it's a completely different problem, but that's the direction we're headed. And so I think that's important for industry here to say, like, hey, we have to model that, and it's a completely different environment, like a space enclave, where we could model.
Yes.
But they also need space effects modeled, so some services
correct.
would include. So we're working both, services
that's great.
or other domains within the main problem.
So we're actually embedded in GSC, right? And at unclassified level, what we can say is the current math model of how it's built, because it's based on our databases in many ways, is already understanding the true geoid. When the satellites come right on the horizon is when you want to detect. The shape of the Earth is correct. So you should be able to exploit that, and the NGTS people already has part of the model for the line of sight for that. But in my opinion, both the Amman swarms plus space has to be part of this, because we need to communicate with space too, in narrow beams too. So this is not, you need all of them at once. The battle space is no longer at 1 kilometer thing with a radio. This is like thousands of kilometers away, everybody with sensors, everybody attacking each other, and many of them autonomous. It has to be tested in a synthetic environment at a scale for millions of hours to be efficient in the battlefield when it comes. Hopefully it never comes. But.
So, great. All right.
Yeah, sorry,
folks.
I always talk too much. But,
unfortunately, I see we have one more question, but we ran out of time, so that was all the time we had for today, folks. Brian, Javier, thank you. It's been a pleasure. Thank you, folks, for joining us.
Thank you.
Yeah.